Yes, today's the last one you'll have to suffer through. Right, so I think today I'm going to just continue along the line of the topic I was talking about over the past few days and try to draw it to some conclusion. Originally, when I had more ambitiously thought that I would go at about twice the pace that it went, I thought I would tell you about some somewhat related string theory construction, but I think it's too ambitious to talk about that today. So I mean, unless at the end of the hour somebody wants to hear about it, maybe we can talk later or something. So at the end of last time, we had gotten to this point where we added some end-of-the-world brains to this JT gravity theory, and then we wanted to compute what effect they had if they were dynamical objects. And I mentioned that a kind of basic one kind of contribution that if you add end-of-the-world brains, there's something that looks like a trumpet like this, where the end here has length b, and here's where the brain sits. And this integral at small b had a logarithmic divergence of this type. And the way to think about it is that in addition to these objects, you add to the theory some cusp instantons, or we could imagine that that there's some very heavy matter which modifies this answer at very small b. Okay? Because there's a small cycle here. And all of those contributions are in this near cusp limit. And in fact, this was studied previously, and I'll come back to its interpretation in a bit. Now, we can, putting that aside for a moment, what is the full effect of adding these objects in the Euclidean path integral? Right? So in the story of SSS, they sum over all Riemann surfaces with handles, any number of handles. Here we'll also sum over any number of these geodesic end-of-the-world brane boundaries. And what happens when you try to put the whole thing together? Well, it's easy to figure out what that does in the matrix model. If we go back to how the SSS model worked, every time you added a nearly ADS2 boundary, you inserted a factor of trace of the matrix. Trace of the exponential of the matrix, right? So they had this matrix integral schematically like this. Again, the potential was double scaled, so this is a little bit of a abusive notation. And then every time you had a nearly ADS2 boundary, you would add a new factor like this for each ADS2 boundary. Now we want to add a different kind of boundary, which looks like this end-of-the-world brane. And it's very natural to think that every time you add an end-of-the-world brane boundary, you'll add trace of a different function of h. Okay? And it's easy to work out what that function is. Basically, you just want to take a kind of inverse transformation. So the duplicated contribution with many handles. It has a bunch of ADS boundaries. And then you want to add on to this thing one additional end-of-the-world brane boundary. Okay? Now, instead of putting an end-of-the-world brane here, we could have glued on one of these trumpets. Then we know what to do, right? Because SSS told us the answer. So what you would like is to remove the trumpet part and replace it by the measure you get from this end-of-the-world brane. So in other words, when you put this trumpet, it depends on the inverse temperature beta. What you would like is to find the inverse of the trumpet. In other words, a function like this, which depends on b and beta, and then put here some z tilde, and pick z tilde. Maybe I should call it f. It's not really a partition function. It's just sort of an inverse transform. Pick f such that this thing is equal to the answer that we want, namely the measure associated with the end-of-the-world brane over b. And this measure is given by e to the minus mu b. That part is obvious. And then there's the piece that came from a one-loop determinant that looks like 1 over 2 sinh b over 2. Okay, so, well, if you try to actually write this f as a function, you have to move the contour over beta in order to make it converge. But one can feed through those functional transformations and work out what you will want to insert for the end of the world brain. So the point is, we know in the matrix model that if we put an ADS boundary, we would insert this object. So instead, we should insert trace of a different function of h, which is given by integral d beta, e to the minus beta h, f tilde, I called it, or whatever, of beta. Okay? Does that make sense? Yeah? Okay. And so one can compute what that is. It turns out to be a pretty simple computation. And I'll call this the potential that you get for the end of the world brain. And you'll see why I call it a potential in a second. And the answer of that integral is minus log of gamma function plus mu plus I square root 2 phi h times this same expression with the minus sign in front of the I. Okay? I write it like that instead of absolute value squared because it might be that this, I mean, we don't know whether this, we may analytically continue this, but that's not a real number. Okay, so that's what we should insert. Trace of v of h is what should be inserted to add a single end of the world brain. But this thing is supposed to be a dynamical object in the theory, unlike the ADS2 boundaries in the SSS case, so we're supposed to sum over adding any number of them. And so therefore, we should exponentiate the trace of this thing and insert that into the matrix model, which is the same as changing the potential in the matrix model. And so the end result is that we will have a matrix model that looks like the SSS potential plus this extra potential. Okay? And now if we do computations inserting trace e to the minus beta h into this, it will compute the thing with those fixed nearly ADS2 boundaries where I sum over any number of end of the world brains. Okay? Well, it doesn't because this thing is, I mean, it's the magnitude squared of this, so it's a real, I mean, if h is real, it's real. If h is real and positive, it's real. I just wrote, I mean, okay, we can write it like this, but that might be slightly ambiguous if we think of analytically continuing h, but yeah, you know what I mean. Yeah. Okay. So that's the answer. Now, we could also consider a situation where we had many species of end of the world brain, say all with the same tension. Like, for example, if we imagine it's came from some kind of brain in a higher dimensional theory, maybe has some world volume theory, its quantum mechanics has some degeneracy, so we might add k of them, and then I can put a factor of k here. And it will be interesting to consider a limit when k is very large, in fact. At least that's when the effect of these brains is most significant. Right, so I didn't really define what I meant by this, but this is a double-scaled model, so you should think of the counting parameter here as being e to the s naught, but the size of the matrix is infinitely bigger than e to the s naught, right? But this is the thing that you keep finite in this potential. And so this model is sort of interestingly different when k is of order e to the s naught. Mm-hmm. Right, and in fact, you can think of obtaining this by integrating out some fundamental matter, and so an alternative way of thinking about what it did when you added these end of the world brains is I can produce a state like by doing a Euclidean path integral like this. Here's the ADS boundary. Here's my end of the world brain boundary. Let's say I have k species of them, so I have this label I, which runs from 1 to k. So if I take a particular one here, this produces some state. Okay, and then I can evolve in Euclidean time by some amount beta here. This will produce the state e to the, let's say this length is beta. This will produce the state times something, right? Whatever is the state that kind of has this end of the world brain in the interior, okay? And in the same spirit that the pure JT gravity looks like some random model for what the Hamiltonian of this quantum mechanics is, when you add this object, it's like a random model for what these states are. And so we could say that instead of writing that, we could have sort of derived it from a more matrix model point of view. We could have said we had just the SSS model. And then we also added these fundamentals, which now have the interpretation of states in the Hilbert space of the dual theory. And they would appear with some action like this, and it turns out that the object that sits here is the same gamma factor. That's what I was writing.
Sorry, I came a little late, but
Oh, you mean where does the gamma come from this point of view?
matrix of some saturated. So
Right. I mean, this gamma comes from a computation in JT gravity. It's basically the what's the right? Well, okay. So over here, this. So I explained how we computed this. This came from the trace over there, and in this picture, the thing gamma is basically the normalization of the state. Comes from the normalization of the state. Okay.
the ratio of gamma of the conjugated.
That's true, but that might be a coincidence. I don't see a direct relation. I'm not sure. Yeah, I'd have to think about it. No. Okay, so then if you integrate it out, then if we imagine that we don't care what these states are, we think about integrating them out, then you get that effective potential. Okay. Good. Actually, there was a paper by Douglas Stanford and collaborators where they thought about introducing end-of-the-world brains in JT gravity, but they didn't treat them as dynamical objects. So they weren't integrating the loops of them. But this same factor appeared in that story because it just comes from the normalization of the states that you'll make like this. Okay? So it was kind of not a surprise that this comes out. Yeah?
They also had a matrix model without.
Well, they wrote some kind of matrix model. Well, I don't know. Come back and mention something about what they said in a little bit. But if you write, this is the only matrix model you can write in this context. And if you write this matrix model and you integrate out psi, then you'll get that. And they didn't. And if you do that, that means you integrated loops of them. In a sense, their thing was like you don't exponentiate this, and then you just insert it when you did some computation with the end of the world brains. But that means that they treated them as external objects. Not dynamical objects that you summed in the theory, but some gadget that they threw in by hand in a particular computation. So I would say although they called them dynamical, they didn't treat them as dynamical. Okay. Of course, this shift of the potential here only matters if k is of order e to the s naught. Otherwise, it's a subleading correction. But in fact, in their context, they considered k of order e to the s naught. The reason why that's interesting is because interesting to think about is from some point of view that's a little bit too naive. You might have said e to the s naught was supposed to be the extremal entropy in this JT gravity theory, right? If we took the JT black hole down to 0 temperature, it has entropy s naught. Where does that entropy come from? So since all the configurations look like the JT spacetime ending on something, we might say maybe that's the entropy of just the number of end-of-the-world brains. Now it sounds like how it works in string theory, right? The extremal entropy as computed on the gravity side matches the degeneracy of brain bound states. So you might have thought that this k should be of order e to the s naught. Okay, so that's kind of a natural picture, but there's something about it. well, there's some subtleties, so we'll come back to it. Okay? Right. So, interestingly enough, I think I skipped a formula that maybe I should have written. Right, where did this log thing come from as an integral over b? It's slightly useful to write that. Let me just write that here, and then I'll move this board up. I think that was from last time, and it didn't get erased. It's interesting. Okay, so our potential v, if we wrote it as the integral over b, this is how we got that gamma factor, would look like this measure for the end of the world brane over b, cosine of b square root 2 phi b h. So this cosine factor is basically the trumpet with the 80. It's like the thing that would connect a guy with length b, and then on this side project onto energy eigenbasis instead of putting the thermal circle here. That gives you this cosine factor. Anyway, this integral, that integral has a divergence at small b, but it's an uninteresting divergence because it doesn't depend on h. Okay? So the divergence comes from the term in the 1 in the cosine, which is an h-independent term, which is a number. That doesn't affect the matrix model at all. It's an overall factor. It's just the overall normalization of the matrix measure, so you simply throw that away. And then the term which comes with h comes with the b squared, and remember, m of b looks like 1 over b, so that term is finite. And indeed, this log of gamma is just some finite function. So the deformation of the potential is actually perfectly finite. It doesn't have this UV divergence that I mentioned before, but the divergence is going to come back in a somewhat different guise. Okay? So now what one could try to do is to solve this matrix model, or you could do it the whole computation on the gravity side and use topological recursion with boundaries, and you get the same answer. And we checked that. Yeah. So somehow it looks like at the level of this change in the matrix potential, the divergence disappeared because it was an h-independent. Well, another way of saying it is, although there was the divergence in this partition function, as a function, when you computed this thing as a function of beta, if you extract out of it the spectral density by going to energy basis, then it didn't have a divergence. So it was sort of overall trivial divergence. No, it's not really. Well, that's always the case in a double-scaled model, of course, strictly speaking. But the divergence comes back in a different way, and I'll explain in a second. So then one way to solve this problem is to try to solve the matrix model. So this change in the potential. So note that VSSS is not well-defined point-wise as a function, right, because it was a double-scaled matrix model. But this change in the potential is well-defined point-wise as a function. And so, although we usually think of solving matrix models all at once, you can also, and in this context it's a bit easier, to imagine you know the solution of this double-scaled potential, and then you find the change in the spectral density from this change in the potential. And then you'd never have to think as hard about the double-scaled limit, okay, because this is a point-wise finite function. And there's a little subtlety in doing that, which is important, and I'm going to come to it soon. So this should result in some change in the spectral density, well, not necessarily proportional to k, but anyway, a change in the spectral density. And one can try to compute it with standard matrix model techniques. Okay, so write the usual formulas for the resolvent and the et cetera, and I won't review how that works. But let me just explain to you qualitatively what it does. What does the force look like from this potential? It's log of a gamma function with this argument which has an imaginary part that's growing with square root h. And if you work through it, you'll find that it looks like a constant force on the very large eigenvalues. So for the large E eigenvalues compared to the SSS balanced distribution, this new thing gives a force pushing the eigenvalues down. And that leads to a divergence in the answer for delta rho when you summed up everything. Okay? Basically, the original distribution was this sinh square root 2e, roughly. And now there is some constant force pushing this way. And if you work it out, you find that it pushes down a logarithmically divergent number of eigenvalues. Logarithmically divergent in where you put the UV. If I cut the spectrum, of course, at a finite place, then there will be some equilibrium distribution having changed the potential. But it will look logarithmically divergent in where I put this cut. Okay? That's the same divergence that one saw in the direct computation. Okay? Now, well, because it's a double-scaled model, right? So in other words, if I put a cutoff here, then I will find a new distribution. It's just that the density down here will depend logarithmically on where I put this cutoff. Okay? So in the limit that I remove this, this on its own seems somehow puzzling. Okay? But there's an explicit formula in terms of some Bessel. I'll write it down in a minute. No, it's exact. I mean, right. I mean, if K was tiny, then anyway, the most interesting case is when K is of order e to the s naught. So we worked that out. Okay. Now, there's a slightly tricky thing, which is when you have a double-scaled matrix model, the total number of eigenvalues is infinite. So normally, when I try to solve for the eigenvalue distribution of a matrix model, I have a fixed number of eigenvalues, and I use the normalization of the spectrum, that the total integral dE of rho of E is fixed, and that fixes the endpoints of the eigenvalue distribution. Okay? But in a double-scaled model, this is divergent. It's not normalizable. So you kind of lose this condition. And so here, of course, if I took an undouble-scaled version of the SSS model, where I fix the total number of eigenvalues, then I play this game, things will shift down. But that's not really the physically right question from the gravity point of view, because it demands that when you added some new objects, the total number of states stayed the same. And that's a completely unreasonable thing to ask on the gravity side. That's not what you would have demanded, right? The total number of states is an output from the gravity point of view. So what is supposed to set the range of S? The logic is inverted, right? They knew the spectral density to start, and then the part of the definition of the model was that you take the double scaling limit in the right way so that the distribution starts at 0. But now when you add this term, what you learn is that you have to take the double scaled limit in a slightly different way. In particular, you need to shift the constant term in the force or the linear term in the potential by an infinite amount in order to readjust the distribution to end at a finite position. Another way of saying it is if we just took this naively, it would push the eigenvalues all the way up to minus infinity. Okay, so you need to adjust. So one of the coefficients here is a linear one, and its coefficient that goes to infinity in the double-scaled limit, and you need to take it to infinity in a different way when you add this. Okay, so we sort of need to modify the double scaling. And then you might ask, what's supposed to determine the answer? Because if I modify it in various ways, I can set E naught to be any number. So E naught is supposed to be the minimum value of the eigenvalue distribution. And now this relates to a related fact that people studied in the context of a more general W phi gravities that I briefly mentioned last time in answer to a question of Zohar, but let me elaborate a little more. So, oh, yeah. Okay. Right. Well, I'll tell you a theory where it would have a different answer. I mean, perhaps the W phi gravities don't have the same symmetries. But, I mean, if you write the general W phi gravity, you get a different answer, of course. So, yeah. It's something different, yeah. Yeah. Yeah, it has different symmetries, yeah. Yeah. Well, I mean, so, how should I say it? Of course, the edge of the spectrum always looks like some number, some density times square root E. Okay? That's the true near extremal place. And there's, to get the shape of this cinch of square root E means that the dilettante potential is exactly linear. Okay? Is linear. Okay? So that the metric has just the constant negative curvature period. Well, right, but I mean the general W phi gravity doesn't reduce only to the Schwarzschild. Yeah. Right. Okay, so there was this idea to try to generalize the story of SSS to theories which are a little more complicated. These W phi gravities. That's the guy where the bulk action has this piece, like in JT gravity, but then instead of having just 2 phi, we write some W phi here. So when W phi is 2 phi, that's JT gravity, but we can write something more general. Okay? And it was shown by Witten and maybe some other, in another paper, that if this W phi has a very special type, if it looks like a sum over things like e to the minus 2 pi, well, let me call it e to the minus alpha I phi's, where alpha i's are some numbers, discrete set of alpha i's, let's say, where this guy is between 0 and 2 pi. If I instead of adding this exponentiated to the theory, I just took a single insertion of e to the alpha phi, it will be some defect operator inserted into JT gravity, looks like an instanton, and it's exactly an instanton that creates the conical angle of alpha. Or sorry, well, I don't know how you define the cone angle, but the alpha is the discrepancy from 2 pi. Okay. So, and you can work out how the spectral density changes if you modify the theory in this way. Okay? Now, a curious fact is, and what's relevant in this context is the alpha goes to 2 pi limit. That's where you put in something with deficit angle 2 pi, which is a cusp. And the cusp looks like the trumpets we're adding shrunk to 0 size. That's where the divergences came from. And interestingly, if you try to compute, you can compute delta V of the matrix model associated to adding these conical angles. And it's some expression in general, but if we compute what delta V of H is in the special case of alpha equals to 2 pi, it turns out to be 0. Okay, so when you add cusps, it doesn't change the pointwise, doesn't make any pointwise difference in the potential. It just changes how the double scale limit is taken. And in fact, it corresponds exactly to shifting this E naught. So by modifying the e to the 2 pi phi term in the effective potential, you shift E naught around. Okay? So of course, the pure JT answer has, in a sense, special symmetries. But now we added these end-of-the-world branes. They generate, by gravitational instantons, corrections to the long-distance theory that already make that symmetry not exact. And then, in a sense, in fact, they give a divergent, logarithmically divergent coefficient to the e to the 2 minus 2 pi phi term. So in that sense, it's like a relevant operator. I add something that's very heavy, and it modifies the coefficient a lot. And then I can imagine also adding the pure cusps by some amount which cancels it either in total or in part. Okay? Maybe the most natural thing might be to cancel it in total. That will mean that you adjust things so that you don't shift E naught. But you're also free to add it with some finite amount and shift E naught, because in any case, the effective potential is not just of this form, of course, when I add the end-of-the-world branes, and so I don't have that symmetry, don't have that pattern of symmetry breaking exactly anymore anyhow. So in fact, one can make a kind of effective theory expansion of what potential you get by integrating out the end-of-the-world branes. Let's imagine they're very heavy, so we'll take the tension of the end-of-the-world branes to be large. I can make some 1 over mu expansion. If I have k species of them, I get a contribution in units of k over e to the s naught. Then I have this e to the 2 pi phi, and then I get a perturbative expansion. So the first part is this logarithmically divergent thing that we want to cancel. And then there are perturbative corrections in inverse powers of mu that one could compute, and we computed a few more. Okay? So from the IR point of view and the gravity theory, E naught is just a parameter that is determined by the data of the long distance theory, and then it is UV completed in some way. So okay, so given that, the end result is really that I pick whatever E naught I want, and the different E naughts correspond to different theories. And then I can go ahead and compute the resulting spectral density of the matrix model. I'll write the formula, but it's not very... Well, E naught is just the lowest energy point, the ground state of the spectrum, the edge of the spectrum. Yeah. E naught is the edge of the spectrum.
This is W effective for which?
Oh no, this is the W effective from end of the world branes.
Okay.
So it looks like the cusp perturbative, polynomial times some pseudo polynomial, right? It's some expansion.
Is that this mean kind of symmetry when you shift five?
Yep.
And this cost like
it might actually resum. It probably resums to something invariant because the end of the world brane action itself looks invariant. Yeah. So it must resum to something invariant. This is just this is an expansion when phi is small compared to mu, and that will be violated there. Yeah. Yeah. This is sort of some small phi expansion. Yeah, I think we might have computed exact expression. I just don't have it in the notes. Well, at some point it becomes a little bit subtle precisely what you mean, right? Because you're trying to replace a dynamical object with an effective potential where you integrated it out, and it's not clear. What exactly whether that's a good idea when you start probing scales that are heavier than the object you integrated out. It might just not doesn't really take the form of a W phi gravity. So it's maybe formally you can write something, but I'm not sure how meaningful it is. But right, because it still has, in other words, the W phi gravity still has no propagating degrees of freedom. Right? Yeah. Okay, so well, anyway, the end result for the spectral density is something that's not very intuitive, but I mean, I guess I can write it down.
Actually, what
Well,
conditions in front of R can become function. Then you also need some terminals.
okay. Right, that would be a more general, more general thing, Are you sure you can't remove one of them by field definition? No? Okay.
No observable and zero observable.
Okay. Okay, well, in any case, from the matrix model, you could compute the spectral density, but I'm not sure if this expression is going to be very informative. But if we shift the start of the spectrum to some arbitrary E naught, then we get some function here, some Bessel function. This is kind of the contribution you would have gotten just from the cusps. And then the piece that comes from the end of the world brane, we can write in terms of some function that we called f. And we can, sorry, this is, and then this function f can be written as an infinite series. This is not a very informative formula, I think, but I'll just put it on the board once here. But I can have a typo in this formula. I hope I didn't make a typo in this formula, but anyway, the correct formula is in the paper, but I copied it wrong. But I don't think you're going to learn anything from this particular expression, but something like that. I hope I didn't make a mistake. But so well, maybe I'll answer a slightly different but related question. Whatever theory of gravity I had in 2D, of course, I can imagine trying to study it in the near extremal limit, right? So if I go to ultra low temperatures, then something looks universal. And that's true in any of these models, because that just corresponds to focusing on the very small E behavior of the sense, which looks like the square root of E edge that you'll get from any matrix model. But that actually corresponds to a strongly coupled limit of the Schwartzian, right? Because, Now, in order to see the whole sense, we could also imagine we can also consider another limit, which is a high temperature limit. Okay, and in the high temperature limit, we will probe the physics for very large phi, right? Because phi horizon will be a big number. And in fact, in this theory, the high temperature limit also looks like the e to the square root e. So both at very low temperature and very high temperature, it seems to match the central square root e, but the behavior in the middle can be different. And the reason why the behavior in the middle is different is because for intermediate values of phi, something different is happening, right? Right. So I mean, Well, the phi profile always breaks SL2R. Right? It's not constant. You know, the only SL2R invariant profile for phi will be a constant. So it always breaks SL2R. Breaks it in a different way. But yeah. So the real point is the following. So you might ask, why is there a limit of the SYK model which is described by the cinch? Okay, I think that's maybe the real question. If there are all these other theories which look similar, and they're sort of, why is it that in the SYK model we see the whole cinch of square root E and not just the square root E edge or the E to the square root E high temperature part? Why do you get the whole cinch? And the reason is because of the reason is because G Newton is small. So we kind of suppress the factors of the gravitational coupling in writing the JT action. But if we put them back, then we would have written something like 1 over G Newton times phi r plus 2 phi plus, you know, e to the minus 2 phi or whatever else we had, whatever other terms here we added. And then if we rescale phi and beta and so on to eliminate the G Newton, it will make these terms extremely small if G Newton was small. Okay, so it's really the large N of SYK which makes G Newton to be small, is the reason why you get the cinch of square root A. Here the theory became strongly coupled because we added e to the s end of the world branes, and so it doesn't have, you know, it became strongly coupled in this G Newton expansion, which wasn't, G Newton expansion is kind of hidden in the pure JT gravity because when you don't have anything else there, you can scale it away and it's removed entirely from the problem, but it's really the thing that's telling you that those should have been suppressed. See, the point is that if we restore the G Newtons, this term came from an gravitational instanton. So it really looks like e to the minus 2 pi phi over G Newton, right? Okay. And that's kind of a funny correction and an effective action, right? So of course, if we, in the way that the urge values at infinity, and so even a term like this can become important. Yeah, so that's a slightly funny. The aspect is a little bit funny. So in a sense, we're not really in a semi-classical regime of this JT gravity theory, unless we take some other scaling of parameters. So we could try to rescale parameters, and maybe it can look weakly coupled in the new renormalized variables with some scalings. But in general, it will look strongly coupled, and that's sort of the resolution to this puzzle. Does that answer the question? Somewhat? So let me just tell you one interesting feature of that spectral density, which is if you go and look at the edge of the spectrum, you can read off an effective S naught. Okay, so we can read off an S naught effective, and especially if we're in the regime that K is extremely large, let's say K is even much bigger than e to the S naught, we added an enormous number of species of end of the world branes, then you'll find that the effective S naught looks like log K plus S naught. That formula sounds extremely reasonable. We added K species, and so therefore we shifted the extremal entropy by log K. This is kind of interesting because in the paper of the Douglas Stanford and friends, where they considered adding really non-dynamical end of the world branes as a way to keep track of states, they formed a sort of entropy puzzle where they imagined that you had, when I have K bigger than e to the S naught states, it seems that I overcount the dimensionality of the Hilbert space. So if I think that I have, you know, things with ADS boundary and an end of the world brane, and I have more than e to the S naught species, then I will get some overcounting problem. And they discussed the kind of resolution using replica wormholes. But actually, if these are dynamical branes, the problem disappears in a different way. The effect of the branes corrects the long-distance theory and just shifts S naught up, so it doesn't violate the Bekenstein bound to begin with. So it sort of has a different flavor resolution, whether you thought of these as just some states of the theory, labeling states of the theory but not a dynamical object, versus actually adding a dynamical object. So if you add dynamical objects, then they correct the theory so that the entropy bound is still obeyed. And that's something that people saw when they discussed the species problem in the context of the Bekenstein-Hawking entropy a long time ago and so on. So it really works similarly to that. Okay, so that's sort of the story of this matrix model. And
you call this term e to the minus 2 by 5. Actually looks like just
that was JT gravity with the end of the world, right? So in other words, integrating out this dynamic, the end of the world brings in the heavy dynamical object, and then it contributes to.
What are those things which are heavy?
Well, no, I think here I didn't add fields. I added branes, so it's something slightly different. I mean, if I added fields, I would have perturbative corrections, not only instanton corrections. So because I added these branes, there were no perturbative corrections, only this instanton. I'm not sure if I quite understand. Mm-hmm. I think it's not quite the same as that, because the space ends at this brane where it wouldn't end at a Wilson loop, right? So it's slightly different.
Here the space is something emerging. In the BF interpretation, the space is something emerging. It's a space in which the gauge fields leave, and then when you interpret gauge fields, you find
I guess so, but then somehow in the BF language, you can't really make the space have a different topology than the one that you input, right? I mean,
not every gauge field configuration corresponds to a smooth metric. Topology is change of the topology corresponds to the bind not being positive definite.
Right. But what I mean is, I don't think you're going to find. You won't be able to find a smooth BF configuration in the disk, which makes the manifold look like the trumpet, right, with a hole in the middle. No, but it's not a hyperbolic metric on the disk. It's a hyperbolic metric on a different manifold, right, on the trumpet. So in other words, how can you find a BF configuration on the disk that looks like? Right, you have to put a exactly. So, but right, but then you're doing something which you'd never do in BF theory, which is you change the rules of the game and you say that you have to sum over the contributions on the disk and on the annulus and on the annulus with two holes, etc. And that's not what you do. That's not BF theory anymore, right? That's BF theory coupled to topological gravity or something. In other words, you have to add the sum over topology of the space on which you define your BF theory.
Topology would be changing topology would be interpreting the configurations of the H theory in vector terms, which cannot be done probably.
As far as I know, that doesn't work. So my understanding is, like, let's say we just wanted to discuss the relation of JT gravity in SO2 RBF theory on the compact manifold, compact Riemann surface. My understanding is that JT gravity on a genus G Riemann surface is the same thing as the SL2RBF theory on a genus G Riemann surface with the condition that the first Chern class of the bundle is G minus 1. So it's not that if I sum all the bundles on the genus G Riemann surface of SL2RBF theory, it equals something good. The correspondence doesn't work so beautifully. It's sort of only perturbative. And the sum over topologies on the two sides is totally different. That was my understanding. Maybe there's some clever way to make it work better, but I've never seen that. I think it's, at least I have not seen it. So the sum of the bundle topologies and the sum of gravity topologies look discrepant, and you sort of, the determinant in fixed topological sectors can be related, but which topological sectors you have is different.
Proposing was that you don't identify the wall sheet.
Yeah, no, I understand, but I don't know a way to make it work, actually. Yeah, I don't know a way to make that work. Well, I'm like, for example, well, I mean, there are things that are like that, but they don't work the way you want them to work. So if let's say, take all the SL2R bundle connections with the appropriate boundary condition on the disk, then they're labeled by some number, some integer. Well, in other words, when you take the nearly ADS2 boundary condition, there's a kind of relative Chern class. And if you take the sum, if you take that number equal to 1, then the gauge bundle is related to the disk. But if you take it to be n, it's related to the thing with the 2 pi n cone angle. And you don't want that in JT gravity.
What do you do when you add this?
No, well, but I'm not adding all. I'm not adding e to the 2. I'm not adding all of them, right? So in other words, the thing that we usually do on the gravity side is we have it's just discrepant from the BF computation. So, right, I mean, you could reinterpret the BF computation perhaps as some theory of gravity, but it will be one where you add cusps and the 2 pi n conical excess and so on with specific coefficients, which is not what I'm doing, and not what people who say they study JT gravity are doing. So it will be a different, perhaps also interesting theory, but a different theory. Urgent answer, so maybe it's not such a good theory when you add all of those, but I don't know, maybe, yeah. So there's something different about the sum over topologies, yeah. But yeah, maybe it's interesting to work out this dictionary more. Okay, any other questions about this? So let me try to just wrap up here and try to pull together some of the different things that we talked about over the past few days. Maybe I'll have to erase something. Okay. So how should it work in a good theory? I sort of alluded to this, but now I can put more of a formula to it. So again, when I say how should it work, I mean, how does the Lorentzian theory, which seems so simple, that canonical analysis, how should I think of all of this rich Euclidean story, which led to a matrix model and so on? How am I supposed to reconcile those two pictures? Okay, remember we had this funny fact that if we thought about the Lorentzian theory, if we have one ADS boundary, we have to end the space somewhere. We'll end it on an end of the world brane. If we just do canonical quantization, the only thing we will contribute is this trumpet. On the other hand, when you do the Euclidean computation, you'll have something that starts with the disk, plus many other corrections, including the trumpet, but also things with handles, and the two sides just don't seem to be the same, right? How should it get fixed? So the idea is when I say the Lorentzian theory would lead to this computation, it presumes that I fixed the gauge correctly, and the inner product is the naive inner product. So in other words, the thing that the Lorentzian theory really told me how to compute was this propagator, which this has length L and that has length L prime, and I evolved by some Euclidean or Lorentzian time beta. That was a clear consequence of the canonical quantization. But it's only if I assume that I correctly fix the gauge that I should take this side and glue it to this side with a delta function that says L equals L prime and integrate over L. And in fact, we know that in general, if I hadn't fixed the gauge correctly, the inner product would look different, right? So this is especially familiar maybe in the gravitational context. When people discuss, these Hartle-Hawking or Wheeler-DeWitt wave function, they imagine they define some spatial metric and other data on a slice, and this, of course, does not fix the temporal gauge. I didn't impose the Hamiltonian constraint equation because I just picked some data on the slice. It would be similar to in electromagnetism to fix the gauge field configuration on the slice only and not specify what happens to a knot and so on. That doesn't fix the gauge, right? But I can still compute, if I had a state that was, say, defined by Euclidean path integral with some boundary and sources, I could still compute the overlap. So I would still be able to compute something like my G with psi, and I can call that the wave function of phi of G. That's the wave function that Hartle and Hawking and Wheeler-DeWitt talked about. And there are two ways that you could think about it. You could imagine taking the Hilbert space, the non-Hilbert space, but the vector space, spanned by these G's as linearly independent vectors. That's like the pre-Hilbert space before I impose the constraints. But another way that you can think about imposing the constraints in such a context is to say that this map is perfectly well defined. And so I can use it to interpret G as an element of the physical Hilbert space. But then the inner product of the G's is not delta G minus G prime. Okay? So we can think of G as being an element of the physical Hilbert space. Well, it's kind of like a covector, but since no, because you can compute this for any in a situation where I can turn on boundaries let's say I'm in an asymptotically ADS spacetime and I turn on sources. This is supposed to be an ADS boundary. I can put any sources that I like, and then I compute this overlap. I think that the states generated by sources span the whole physical Hilbert space, then it will determine this state G. Okay? And then the inner product between two G's, I can also compute directly, and it will agree with the one I would extract from its overlap with any size by saying that I do the path integral with some G here and some other G prime here, and I sum over everything in between. And of course, if I didn't try to fix the gauge at all, G is just the metric on the slice. There are many ways of filling it in with different G and G prime. They might be two different spatial slices of the same space-time. And then I will fill this in with an on-shell solution like that, and it will get a big overlap. So this matrix of overlaps is not delta G minus G prime. And in fact, here, got this one. Let me grab another piece of chalk. I think that eraser has seen better days. So what it means is that the psi of G is a redundant data. Well, okay, so first of all, the fact that these have some non-trivial overlap just tells you the inner product is modified. But in this context, it's clear that they're actually redundant because I can slice the same space-time with different spatial slices. And so there are many null vectors in this inner product. And if I eliminate them, I will see that the data psi of G is redundant, and the redundancy is exactly the constraint equation, which in the gravity case is quadratic, and the metric variation is some structurally something like this. That's the Wheeler-DeWitt or Hamiltonian constraint equation. The distinction with gauge theory is that in gauge theory, the analog of this, if you do this kind of thing, this differential operator will be first order, And because it's first order, you can always interpret it as saying that, just saying that psi is independent of some change of the variables along the slice. So you can fix the gauge by constraining the data on the slice. But that doesn't work here because the equation is second order. So it's more tricky. But here we imagined that we fixed the gauge kind of classically. We said that we picked a geodesic that fixed the local problem. So if we demand that the slice was a geodesic, as we did in the canonical quantization, we don't get an equation like this. But non-perturbatively, in the Euclidean theory, or even in the Lorentzian theory off-shell, saying that the slice is a geodesic doesn't fix the gauge. Right? There may be multiple geodesic slices, even in the Lorentzian off-shell geometry. So if we really thought we were supposed to gauge fix first and then quantize, not classically gauge fix, it may not really have been a good gauge. And we should compute the overlap by adding in all the objects of the theory. And it's sort of completely clear that if we added some heavy degrees of freedom, we would, in computing the overlap, integrate out those degrees of freedom, including if it was something like an end-of-the-world brane. It would be totally unnatural to not, because after all, the effect of the end-of-the-world brane changes the long-distance effective action through the gravitational instanton. So you better plug it in here and include its effect. Otherwise, you're doing something inconsistent with the effective field theory. And so when you compute that overlap, you should really sum over all of the topology and junk that you could put in between. Okay? So now we have these geodesic. So now we can do this in this particular example. What did I do with my spot here? Here we go. So we had these states in the canonical quantization labeled by the length. They ended on the end of the world brane, and then they have a length. So here's the ADS boundary. Here's this thing. They always intersected here transversally. So this is like the t goes to 0 limit of the propagator. Of course, if we didn't put anything here, then because they're both geodesics, and so since the bulk theory looks like JT gravity, it's always geodesically separable. And so we'll get something here, and then this will glue on to the sum over everything else, which might be handles and the end of the world branes, etc. Now, let's suppose that the theory the bulk theory in the UV is something that we don't know. Okay, so we know that it has this end of the world brane, which is somewhat light, but maybe it has many other heavy branes and other heavy objects that we may or may not know. But we sum them all here, and we get some answer. Okay? So I'll call this x of b. B is this length. And we imagine we don't know x of b. Okay? How could it work? So if you do this computation, this piece of it is universal. Just depends on the tension of this end of the world brane and these lengths. This is just a piece of, some path in a row. Actually, there's not much integration to do because there's no wiggly boundary, no ADS boundary, only these things which are geodesics. So it's an easy, relatively easy integral. It turns out the answer for this thing, I'll call it f of L1, L2, and b. It has a factor of e to the minus s naught because I added a whole. And then I can rewrite it. I can write it in the following way. Cosine kb over rho of 2k, where rho is the cinch spectral density of pure JT gravity. I'm just writing it in a sort of suggestive way. And the psi's are the energy eigenfunctions of the Morse potential quantum mechanics with the value of mu, that's the value of mu there. So it turns out this is the answer that you can compute. And what do we learn from that? F is the overlap of the two states if I put a whole of size b. And then the total overlap of the two states is, of course, the I mean, the total overlap of the two states is the delta piece, and then the integral over B of this F with whatever this function here is. Okay? On the other hand, we could also compute the thing that's supposed to be the thermal trace of the dual quantum mechanics. So we can compute Z of beta. That looks like the disk plus the contribution that looks like the trumpet glued on to the sum over everything again. And it's the same sum over everything because we would put that whenever we cut, we're always supposed to sum everything in every computation. And so this piece is also an integral over B from 0 to infinity of this trumpet factor times the same function x of B. And since the same x of B enters both places, we can solve for, say, the matrix of overlaps in terms of Z of beta or vice versa. And it turns out to work in the sense that you get a consistent result. So if you plug these together, that's kind of guaranteed because the thing here came out with these energy eigenfunctions. So the dependence on L is through an energy eigenfunction times another one with the same energy. That's a very special feature. In other words, this inner product looks diagonalized. The inner product is diagonalized by the energy eigenstates of the Morse quantum mechanics, which was the canonical quantization of the theory. And so this inner product looks like the integral over k. K is the square root of the energy. I mean, is k squared over phi b. Looks like the integral over the energy is of the result of this expression gives us what we can write this thing as integral over energy rho exact of e to the minus beta e. So it looks like rho exact of k squared over 2 phi b, so there's a 2 here. The pure answer, just the cinch. And then we have these factors of this size. Okay, so what does this say? What this says is, okay, so first of all, if the exact answer was the disk, then we would have just gotten here the full set of inner products over the Morse eigenstates, and then we would get back delta of L1 minus L2, so that makes sense. So if we don't include any topology, we get back where we were. But if the exact row is the sum of delta functions, then this sum the integral collapses to a sum, and then we would get on the right-hand side a sum over energy eigenstates of this inner product. So this guy, of course, is given by L1k, and this is, well, maybe I should have put a star, but it was real, so it didn't matter. This is that. And so what this looks like is that the matrix of inner products is just a projector onto the actual spectrum that you get. Okay, so if you found, so if you had a 2D, so it's kind of a compatibility condition. So if we have a theory which is JT gravity with this end of the world brane and some heavy stuff, then we can compute what sort of the total spectrum of the dual quantum mechanics like this. We'll get some answer. Then we compute the matrix of overlaps, and we find that all this that it looks like we put the projector onto whatever the spectrum is of that theory. So if we find a magic theory which produces a discrete spectrum like this, it will produce a discrete spectrum in this Lorentzian analysis. So they're compatible. Right. Yeah. Right. So in other words, if you found a theory of 2D JT like if you found a theory of 2D JT like gravity, where the dual quantum mechanics had a discrete spectrum as determined by Euclidean methods, then this kind of universal machine just tells you that although the naive gauge fixing didn't fix the gauge non-perturbatively, when you correct that fact, you get back the spectrum that you were supposed to get. So it's sort of a piece of the answer. It says that there's not some like IR incompatibility. The question of whether you have a good theory is really a UV question. It's the question of whether the sum over all the heavy stuff can produce the right kind of function. Of course, if I write something arbitrary, like pure JT gravity, or some random W phi gravity, or JT gravity with a particular end of the world brane with some random tension, it will not work. Then I will find here a continuous spectrum, and then I will not be able to interpret this thing as producing the same spectrum. Yeah. Well, the condition that on X is the condition that this integral of this with a known function is a discrete sum of exponentials, which is kind of a strange condition, but it's not a very stringent constraint on functions X of B, but there presumably X of B cannot be something totally arbitrary if it comes from a path integral of a local theory. Sure, but what kind of junk would you have to put here to get some particular X of B is not very clear. So I don't have a particular proposal here. But even at this level, you can see a few interesting, a few things, which is if in this story I had said that there were multiple species of end of the world branes, it won't work, because for every species I would get the same, I would get another state, and then I would find k times too many states. That's actually not too surprising, because if I have different species of end of the world brane, that's a label that I can't see from the boundary. So it will be like an internal flavor symmetry of a putative gravity theory, which many people argue shouldn't be consistent, unless the different types of end of the world brane can turn into each other, and then there's other diagrams you'll have to compute, which could then again correct it to this correct answer. And then I turn this sort of very general looking crank, I will get the wrong answer. Okay, so it's not completely trivial that it works. And then there are also other things to check, and it's not completely clear how everything plays out, even at this level, even if somebody gives me the magic X of B. So that's sort of part of the story. There's one other thing I want to mention, and then I'll wrap up because I know I've gone over here. But this will just take a couple of minutes. In the good theory, then, is one where the sum over everything leads to a discrete spectrum and factorized answers, right? But how then should we understand the wonderful success of including Euclidean wormholes in evaluating things like the page curve and various entropies, where it seemed like they were doing a good job, even though there was something a little strange about the way they worked, because they seemed to violate factorization. You know, in other words, I take the partition function of my dual theory on two separate manifolds, it should just be a product, right? So how does it reconcile? And I think the point there is the following. There are sort of there are different orders you can do computations, and depending on what order you do the computation, you may make it look easy or look very hard. And I think that's kind of the way you get to use Euclidean wormholes when you want them, but not use them when you don't want them. Okay, so what if we wanted to compute, say, just z of beta itself, Now there's no second boundary. So we will do some computation. We have this thing, and then there may be some end of the world brains and some other complicated junk and whatever, and we sum everything up. We get some answer. Get some answer like this. Now, in the computation of 2 copies of the partition function, it looks like, I mean, in the gravity analysis, in the bulk analysis, you also have to include the connected geometries and also all the double trumpet and also any other junk. If the theory is of this good type that makes that work, this total sum of everything like that better be 0. Okay. Now, in the long distance theory, that is in JT gravity, for example, there actually aren't saddles of this type. So in the computations that were done by SSS and others, it's an off-shell, it's an integral over off-shell configurations. Maybe you could say there's a kind of the minimum of the action is at b equals 0, which is the edge of the configuration space. So in this computation with these trumpets, there's some geodesic here at b, and the action is minimized when b is 0, but it's not really a saddle, it's just the edge of the integral, because otherwise it's not a manifold. Okay? Maybe you could say there's a sort of saddle at b equals 0, but it's singular. But they can just do the integral. Sure, we don't know. But then that just means we don't know how to do the computation. So in other words, if JT gravity is just a long-distance approximation, we do not know how to do the full off-shell integral. So it could give 0, it could give something else, it could give what SSS said, or whatever. Now, I think if we're in a good theory, it's clear that if we do the whole integral, we get 0. But there was something good about the answer that SSS got, right? It seemed to look like a good answer. It seems sad to say that we should throw it away. That seems to undo the insights that people made over the past several years, right? You know, they had this beautiful story where if you analytically continue to Lorentzian time, so if I take beta to be some epsilon plus it, and beta prime to be epsilon minus it, then it starts out at small t, this square, this is called the spectral form factor, it starts down, and then it grows in this ramp, and then there's this flat region that they call the plateau. The flat region is about z of epsilon. You can think of, if we had a single theory, it makes sense to get this as a rough value, for example, because this thing is a sum of phases, the highly oscillating, and the diagonal ones contribute, and that's what brings it down from a factor by a factor here. And then this is this linear ramp that they discussed. And this feature, especially say this ramp, is matched in a beautiful way by this double trumpet. But if we say that, well, we don't really trust this thing, we have to do the whole off-shell integral over the whole UV, we don't know what the UV is, and in a good theory, when you add up the whole thing, you get 0, it seems to be bad, like then we lost this beautiful result, right? Right, so that's the question. What does the result have to do with good theories? Okay. Now, of course, if we really plotted this function in a particular, in a quantum system where it's factorized, you would not just get this curve. It looks here highly erratic. So there's some extremely erratic wiggles. These erratic wiggles, of course, were never reproduced by this JT computations. That computed some sort of envelope. So when we do an off-shell computation, it's very difficult because you have to integrate over the whole off-shell configuration space, including where you don't know what the effective theory is. But probably in good theories, the off-shell integral is dominated, it can be rewritten as a sum over saddles of the perturbative expansion around the saddle resummed. Let's imagine that's true. Okay, that's a cartoon. So we can imagine that's true. Well, here, because there are no saddles, maybe it's okay that we get 0 because there were no saddles like this. So the only thing that contribute were the factorized contributions. And that's correct because it's the square of the quantity, and the factorized contributions have to get z correct. Otherwise, it's not z, and then we take the square. Fine. That's a fine answer. But what about the good part? Well, we get the good part by asking a question about the averaged quantity. And then there can be a saddle. So for example, so we might do that in a couple of ways. Let me tell you just this, a very simple way. Yeah.
What was the meaning of setting beta to be complex?
Well, that was just to extract this feature that people found to be a lot of interest. Yeah. What does it mean? I mean, well, then you find some complex saddles, right? Right. But I mean, we can imagine we complexify the metric, and now we find complex saddles. Yeah. Just an analytic continuation of those saddles. That's what they did. Yeah. That I think is not too weird. I mean, well, anyway, we can. This is just a particular question. I mean, we could have asked a different. I mean, we could have asked about the, sort of like the 2-point function of the spectral density. Well, maybe we might have naturally wanted to continue beta to imaginary there too, because we want to do an inverse Laplace transform. But maybe we could have thought about it in a different way. We would change the boundary condition to one which projects on the energy, and then we find the real solution. And I think that's more of a detail. So let's suppose that. So here's a way to do an averaging by hand. There are two ways. The flavor is slightly different. One simple way is the following, and I think this. I don't know if somebody said this already or not. I'm not sure. Maybe it's in somebody's paper. If it is somebody, and someone in the audience knows which paper, should let me know. Imagine there's also some matter field in the bulk here. And now we can turn on a source for the matter field. So instead of computing z of beta, we can compute trace e to the minus beta h plus j o, where o is the dual operator of some matter field and j is a source, constant source. And now we can take a product of two of these and do a tiny. This is supposed to be a good theory with a fixed stage. So I say I wanted to compute this quantity, but it had these erratic wiggles, and it's a very hard quantity to compute. The connected gravity contributions, when I actually resum them all, get 0. So it's a red herring that it looked right for the quantity itself, and I have to get all the disconnected ones, and it's horrendously complicated, and I just give up. But instead, I add this little source, and then I do a tiny averaging over the source, say around 0, with some very narrow width. Narrow, but not too narrow. Okay? So now I compute this thing. Now this explicitly couples them. Now there are two ways I could do this computation. I could compute this thing first. That will be tremendously hard and clearly not involve any wormholes because it's just a single trace. And this will be tremendously hard, and then I put them together like this, and I get an answer. But I can also try to solve this problem a different way. Let me do the J integral first. Okay? When I do the J integral, it's like I added a term to the Hamiltonian that looks like a squared O prime. Or maybe I should call it O left, O right. A double trace deformation. What does that do to the gravity theory? Well, we know what it does. It changes the boundary conditions for this matter field in exactly the way that we studied in the context of this traversable wormhole. Here this is a modification to the Hamiltonian, because we just compute this trace. We think of it as a modification of the Hamiltonian. So it's turned on all the time. So it's like the setup that Maldacena and Xiaoling Xi studied, that they called the eternally traversable wormhole. We and they looked at this kind of Hamiltonian in Lorentz signature. What they found is when you have your Hamiltonian is h left plus h right plus this thing, it has a gapped ground state, which is not the black hole. It looks more like global ADS2. And then if I compute the thermal trace, which is what this computation is telling me to do, so now I can of course write this as one trace over the tensor product of the two Hilbert spaces, right? And this is the same as They're just decoupled, right? But then when I integrate out J first, it's like I added this interaction term to the combined Hamiltonian. And then I compute the trace over this thing, and the geometry that contributes is the double trumpet. Uh-huh. It's related, except that I don't think, I mean, they were discussing it, I think, about the original ADS vacuum. They didn't find, I think, this vacuum of the combined system, did they? Or, I don't remember. This is an old paper you're talking about, right? Yeah, yeah. I don't think they found this, but.
What's the temperature of that combined?
Oh, well, I mean, it depends how you rescale, but I don't know. I mean, we could take the two betas to be the same if you want. I mean, or we can say that the Hamiltonian is this one plus 3 times that one, or whatever. This is some details, okay? When we take the two betas to be the same, then it maps to the case that's well understood. And in particular, also in the Euclidean analysis, you find a saddle if I compute the one loop effective action of the matter field first. Okay, so there's this, the matter field dual to O. It has this funny boundary condition that coupled the two sides. I compute the determinant over this field phi with the funny modified boundary condition, and that results in an effective stress energy tensor, which makes this into a saddle. So I think if we think in terms of saddles, what we see here is if we look at this expression and we analyze it by first fixing J, then we'll find factorized saddles, which are very complicated. But then if we do the J integral first, we shift where the saddles are, and they move into a different branch of the configuration space, which looks like this. Of course, the answers are very close in a certain sense because of, continuity and adding this thing. But, I mean, they're not, something a little bit, when A is exactly 0, it looks like this something erratic, so it's a bit different. But no, I had two boundaries to start with because I had these two. Well, that's true, but who cares? This is supposed to be gravity computation. Gravity computation says that this is supposed to be. I mean, in the gravity side, I always sum everything with the boundaries, whether or not I couple the boundaries. Okay? When I couple the boundaries, it just says that the boundary condition couples this one to that one, but that's fine. I mean, from the. Well, I mean, I can draw this boundary on top of that one if you want, but it doesn't change anything about the bulk picture. You can draw it like this. I would not. I don't. I think in this context, nothing is gained by drawing it like that. But if you would like, you can draw it like this.
Question that you originally had two different betas.
Yeah, sure. But I mean, it's easy to solve that because I can put here beta prime. I can put beta times beta.
Becomes another parameter.
Sure, which is the relative weight of the two Hamiltonians. They studied 0 temperature. I think they actually just also missed something because if in this situation you have h left plus h right plus the double trace, if you find the ground state of the combined guy, it doesn't look like what they said. I mean, they sort of studied a small perturbation around the factorized vacuum of the two original Hamiltonians. Also, a difference here is that in their context, their original H had a gapped ground state, whereas here my H didn't have a gap. So it's a different type of system. But if you were to study, even in the case where H had a gap, the same thing, as long as you made this coupling big enough, then you could get into this regime. Okay, but they weren't in that regime. They were in the regime where the space looks split. But Why would it surprise you? I mean, the ground state of H left plus beta prime over beta H right will depend on beta O and beta prime, right? Yeah, plus. Of course, the ground state of this thing depends on all the parameters. It does depend. Well, I mean, the ground state of this Hamiltonian depends on this parameters. I don't know. It's just a sleight of hand. Anyway, in this context, I didn't want to find the ground state. Anyway, I wanted to compute the thermal partition function, right, with inverse temperature beta. So that was an aside about the ground state. Another thing you could do, which is maybe in a way more primitive, is just do some averaging over beta, or an analogous microcanonical averaging over the energy. That will also, if you think about doing that first, lead to a boundary condition now for the metric, which is different. You'll get a different boundary action than just the two decoupled Schwarzians, and it can again have a saddle. So I think somehow in the good theories, what happens is that the saddles shift around. If I do this little bit of explicit averaging, the saddle will shift, and it will live in the space of connected geometries, which is good because that's gave a beautiful answer that worked. Once you do that, the saddle will sit at some particular value of b, which is not 0, and then you will feel like you trust the saddle in the long-distance effective theory. And somehow in this way, in the good theory, you get everything you want. Okay? But the hard part is, what is a good theory, right? How do you construct one? That's a very hard problem, because if I write something arbitrary in the bulk to get, even if it's UV complete, it will not have these properties. It will lead to a disorder average of quantum mechanics, or it will lead to Lorentzian Hilbert spaces with continuous spectra. It's something very special about the UV of the bulk theory that makes all this work. But if it works, you kind of can, in clever ways, by focusing on, say, where the saddles sit and doing, of course, where the saddles sit in the path integral depends a little bit on the endlessly difficult. Then I do the integral over here, it will be very hard. I won't be able to get any simplification, but I do it the other way, then it can be much easier. So sort of I think the picture is like that should explain why everything that we usually do worked, but it works because of something very, very special about the UV of the bulk theory. And I think it would be really interesting to understand better what that was. So I think I'll just end with that. Sorry I went a bit over today, but since it was the last one, I wanted to just come to a kind of punchline. A thing that I would have told you if I had more time was some example in string theory where first of all, we might see something about this factorization problem work more explicitly. So this idea of ER equals EPR is the same kind of statement, right? It's the claim that the states that look like they have two asymptotic boundaries are redundant with the states that look factorized, right? So this state and these states are not linearly independent, but redundant. So this is equal to some entangled combination of these. That's the bulk version of this claim. And in some string theory example, you can actually see a duality like this. So maybe, in some theories like that, we can really understand how it works. In this context, and this is, I don't have it's really work in progress, but you can try to study this double trace interaction from the world sheet point of view, if this was, say, some bulk ADS3 string theory. And the virtue of that is that in the gravity truncation, the things that look connected and things that look disconnected are in sort of different components of the configuration space. So it's very hard to understand in detail how the saddles move from one component to another component. They seem to be things that don't talk to each other. But if we studied this kind of question where we discuss the dual in string theory, then there was a paper a long time ago by Roney and Silverstein and others, and I forgot, I'm sorry, where they studied these double trace interactions in the string world shape. They look like some bilocal thing on the world shape. And I think in the configuration space, so to speak, of bilocal world sheet theories, where you didn't yet impose the beta function equation, so that's like the off-shell configuration space of the strings, roughly speaking, then you can see something connected like this being in the same configuration space as the disconnected but coupled thing. So we have configurations that are disconnected, target space is disconnected but the boundaries are coupled, and here where the target space is connected and the boundaries are coupled. That's what appears in this problem. This thing and this thing in gravity look like they sit in different pieces of the configuration space, but I think in string theory they're sort of in a single connected component, and maybe it's easier to understand there how this kind of moving around the saddles could work. But that's something we didn't do yet. Okay, so thanks so much for listening. I mean, I don't know. Is it, sorry?
Only one parameter, which is phi naught. This is what's missing in the quantum mechanics.
Oh, I see, yeah. Phi naught is what's supposed to set sort of the density, yeah. That will replace, right. Yeah, exactly. Then it should go back to the Liouville quantum mechanics, yeah.
Points in quantum mechanics later should
yeah, I'm not totally sure. I mean, there's this Q deformation, and but that does something even in a way more drastic. It makes the range of the spectrum finite. So it's more like in other words, what I imagine here is something where the spectrum is sort of discrete, but it still goes from 0 to infinity. But in this Q-deformed Schwarzian, and I guess there must be a quantization of it, that some modification of the Liouville quantum mechanics, although I'm not exactly sure what that modification is. Probably it's known, I'm not sure. That has a finite range of the spectrum, but I think it still has a continuous spectrum in the limit. So that's sort of not the, that's like that's a different direction, but.
Spectrum which goes up to
infinity. Right. Maybe you were suggesting the other day that the natural way to do that is to make the kinetic term different, the momentum term different. Yeah. I mean, if I do it by changing the potential, it sounds very peculiar because I'm going to make the potential not go to 0 as L goes to infinity, which sounds very unnatural.
Region in the L space where it's
Right. But somehow that sounds very unnatural on the gravity side. So I can't imagine what I would do on the gravity side to do that.
The side would be, so when the effects of phi 0 take place, that's where the topology kicks in.
Right. I mean, somehow the picture I had was a little bit more like the theory is still described by the Liouville mechanics. It's just the subspace of the Hilbert space. Because the states of the Liouville mechanics included states that I was supposed to have removed by the gauge fixing. So in other words, I can take the Hamiltonian to be the same Hamiltonian, and I could take well. In other words, the thing that's wrong, really, from the gravity point of view, is L isn't an operator. It's not really that the potential is modified so that at large L, the potential tips up. Like that would seem to not, that would be a bizarre IR modification of gravity. It doesn't seem to make much sense.
L matches with L on the gravity side?
Yeah, L is just the length, it's just the length, right? The length of space. So it would sound very strange to take this potential and modified at very large L, it's like a weird infrared modification of gravity. It sounds like it would look.
Those are kind of renormalized.
Yeah, that's true. Yeah, yeah. But anyway, it's still some length, and the L large region is the one where all of the complicated junk is extremely far behind the horizon. So these configurations look like some, from the point of view of the ADS boundary, it looks like something with a horizon, and then extremely far behind the horizon, the space ends, and roughly L is the size of the interior of the black hole. So it kind of makes sense that when the black hole interior is extremely large, somehow you don't produce new states anymore. Like Lenny Susskind discusses this in terms of maximum complexity and so on. But it sounds, it's too coarse to just say that I will, add a term here that's like going to grow as L goes to infinity. That sounds weird to me. I don't know how you would achieve that by local rule on the gravity side. I think it's more like L isn't a good variable because it's supposed to be the length of this geodesic, but that specification didn't obey the constraint equation. L isn't really a gauge invariant variable. So I'm not supposed, so you see, if I modify the potential in terms of L is still a good variable, but I just have a different Hamiltonian. It's something, I don't think that's not quite how it works. It's more that L isn't a good variable.
L was the gauge invariant. Large L was the geometric regime. Large L is whole.
Yeah, I mean, well, L looks sort of in perturbative gravity, L looks gauge invariant, but it's somehow not non-perturbatively gauge invariant in a very subtle way. I mean, it's somehow that like there are relations, like there exists some functions f, such that integral f of L is 0 as a gauge in the physical Hilbert space. So that's somehow the problem, except that these f's have to have enormous range. I never see this funny redundancy. But I, in the end, overcount the Hilbert space by an infinite amount.
That sounds like extremely large L. Something has to do.
I agree. Yeah, something gives, but okay, that's fair. But that's sort of like putting a hard cutoff, and okay, I don't know. I understand, but I don't know. I would be surprised if it could work like that. But, yeah. Oh, well, I mean, in general, of course, I don't know how to find the gravity. If you write me random quantum mechanics, won't know how to give it a gravity interpretation in general, right? I mean, maybe somebody can. Somebody can, perhaps. Uh-huh.
The boundary conditions for fields?
Right. They couple the two boundaries. Yes. Yeah. Yes. So I can draw them on top of each other. I mean, it's connected by a wire. Like a quantum wire. Right. It's this is a large N. I mean, imagine the way a guy will make it in the laboratory is this is his large N quantum dot. This is the second one, and he connected by a wire. Okay, so I didn't draw the wire. Well, it's because you see, I wanted to focus on the emergent gravity part of it, which sees two boundaries. The gravity part doesn't care, I mean, of course it sees that the boundary condition couples the two boundaries, yes. The boundary conditions are coupled, yes. So, okay. Fine. I don't care whether we call it. I guess the purpose of the picture was to represent. I think we all agree on what's the equation. So I mean, I can draw the picture however you want me to draw the picture.
boundary, what is its length? Is it beta or beta prime?
No, I think I think the distinction.
Now we can discuss it.
The distinction is whether the thing, sorry, the distinction is whether it looks kind of like this or this. Okay, like a torus or like a sphere. That's the distinction. They drew this, and here I'm drawing this. And I think it's relevant in different regimes. So this is the correct picture if our H left and H right have large gaps. They have a gap above the vacuum. And I add this coupling small coupling, okay? And A is smaller than the gap. Or roughly order the gap or smaller or whatever. That's this. Here A is much bigger than the gap because the gap is exponentially small. Well, okay, I meant it to be A, but we can write alpha. I would write alpha like this. But, right. So it's a non-trivial question, but it turns out that the ground state. So here we're discussing. So we're discussing a different problem. Now we're discussing the ground state, right? Which was not this question. I'm happy to discuss either one. You tell me. If we discuss zero temperature, that was the context of this old paper, right? So they discuss zero temperature, there's a gap, and then they add this thing where the coupling is smaller than the gap, then you get this. If I have a theory with zero temperature but no gap, even at zero temperature, and then I add this coupling, then the ground state looks very different. I can explain to you how the ground state looks. And why it works like that, okay? So here's the original spectrum of H left. Starts at 0, and then it's very fine spaced. Okay, same for H. Now we want to find the ground state of H left plus H right plus alpha O left, O right, okay? Now, there can exist states where O left, O right has a sizable value. Okay, what kind of state? In what kind of state will O left, O right have a big or reasonable expectation value? Non-zero. The state which is something like the thermofield double state. It has to be a state which correlates the left and the right in order for this guy to have a non-zero expectation value. We imagine that the one-point function is 0. If there was a one-point function, that's just the overall shift of the energy, we discard it, okay? So let's suppose we look at the thermofield double state with inverse temperature beta. Okay, then in this state, I'm going to call this state beta. Then O left, O right has some expectation value which is not 0. Okay, it depends on the temperature. And some function of temperature. And in particular, as we go to lower temperature, well, as we go to higher temperature, this correlator will increase, right? I mean, this 2-point function will get bigger as we go to higher temperature, okay? And so now now, of course, the sign depends on, of course, I can get either sign, right? Because nothing told me whether, I could just apply some reflection to one of the systems. Let's say there's a symmetry, O goes to minus O in the original theory, okay? That's why it had 0 Vev to begin with, okay? So we can get either sign. Let's say we make the choice of TFD so that this comes with a negative sign, okay? Or we flip the sign of alpha, okay? So now we have a competition. If we look at factorized states, this thing will, typical factorized states, this will give me 0 expectation value. Yeah, factorized energy eigenstates, this is going to be 0. And then the minimum I can get is 0 energy, the original ground state. But now, in this kind of state, this thing can give me a negative number. And so, but there's a competition, of course, because I start to turn on the temperature, the original energy goes up. And in many examples, as I look at this class of states and I compute the energy of this H total in this state labeled by beta, it starts at 0, and then it goes down and then goes up. And there's a minimum here. And that leads to the gap, to this gap. You can actually see the same thing in a kind of gravity analysis. Well, but the point is, it says that the ground state looks like the TFD state. Okay? The thermofield double state. And the dual of the gravity dual of this state is not, so in Lorentz signature, we're kind of drawing a Lorentzian picture now. You know, they would have drawn this in Lorentz signature. But now we get something that if we take this state and we delete the coupling, okay, then I would draw the two boundaries as separate, and I would draw this kind of eternal ADS2, and then the coupling coupled the two sides. And in fact, you can find, well, the wire is there when I have alpha, but I can discuss this state in the original. I could take the state that I get here and then delete this term in the Hamiltonian and discuss it as a state of the combined system. Then it would look like a two-sided black hole. Okay, but it's connected. Then we put alpha back. It makes it turn into this. That's the wire, and that makes it. So if I took this state without alpha, it would look like this. And then I connect these two with the wire, and it turns it into this with this joint. Okay? Yeah.
You're really saying something very interesting about the idea of 5 times the wire with a big alpha.
Yeah, or if you heat it up a bit. So there's some competition. So right, of course. But if you, alpha has to be big enough. Yeah.
Okay, you're saying something about a very large alpha.
Yeah.
Can it be verified that you get 5 times the wire?
I would imagine. In fact, there might be some papers about it already. I'm not sure. It's a little hard. As you go up in dimension, it sometimes becomes harder. Like the saddle is less favorable when you go up in dimension, and I'm not sure the exact detail, but I think people may have studied it. I mean, it's harder to make the saddle better. You might add many such operators. So we might modify the coupling like this and make the I have a large range. Right. But I mean, we can. So there are different things you can do. I mean, if do you want to demand the coupling looks local, or do you allow me to couple different modes and in a non-local way on the boundary? We can do different things, and sometimes this saddle is favorable and sometimes not. It depends on details, right? Yeah. Right. But two copies. So the point is, if we take 2 copies of n equals 4 super Young-Mills, coupled in an appropriate way like this with a big enough coupling, and if we're in the right regime and whatever, then you can find solution like this, probably.
It is about n equals 4.
And in n equals 4, I'm not sure if somebody wrote a paper or not. We'll have to look at the literature.
Just big enough.
No, I mean, it is kind of, I mean, this is a configuration, on the gravity side, it looks like a configuration which is supported by a one-loop correction of the stress energy tensor. So in that sense, it violates the large n counting, but sometimes you can find the solution anyway. It helps if you have many, if I have n O's, it would help. But even without n O's, I mean, it Right. I mean, that's kind of clear because the thing that you modified from the ADS point of view is the boundary condition on some field. The field equals to 0 still satisfies that boundary condition. So classically, it doesn't do anything, but it changes the one loop determinant, which can source the stress energy tensor and allow this funny configuration to appear. So it might be that in ADS5, if I do it with just 2 simple operators, I get something that's sort of stringy in here, but I'm not sure, it depends on the parameters. Right. It's sort of like the Neumann fall-off for one equals the Dirichlet fall-off for the other. Exactly. Yeah.
I have 2 copies of
Well, that's not always that's not always the case, right? I mean, so I think people understood for a long time that say the thermophile double state in two copies of n equals 4 will be due to the two-sided black hole.
Black hole has two boundaries.
Right. But it's a single component of the space with two boundaries. That's the picture here. So it's a single component of space with two boundaries. And then you can glue the two boundaries together. But yeah, it's not ADS5. Yeah, of course. This would not look like ADS5. This will look like a traversable wormhole geometry in ADS5. It's only in 2D this looked like ADS2, but that's a coincidence of two dimensions. In higher dimensions, there's a difference about the other dimensions, right? So in global ADS5, the S3 is contractible, whereas in this geometry, the S3 will not be contractible. So it's different. It's not ADS5. It's like the black hole. It's topologically like the two-sided black hole.
Has a parameter which is the temperature, which is the parameter.
Yes. Yeah, that's
There's no sense in which you can decouple.
decouple what? Okay, so I think we're talking about several different things. I want to make sure we're all talking about the same thing.
Okay,
It's very funny state.
it's in a entangled state.
So,
That funny state is described by a
right. Okay, so if we have the two copies of n equals 4 Yang mills with no interaction in the thermophile double state, then it's the two-sided black hole, and the two sides are separated by horizon, and it has a sort of effective temperature on each side. If we looked at two copies of n equals 4 and we look at the ground state, when the interaction is big enough, if we can get into the right regime in n equals 4, which I'm not totally sure, then it will look like, topologically, it will look like the ADS5 black hole, two-sided black hole, where now the two boundaries are coupled explicitly through the interaction, and the wormhole of the black hole, which was before not traversable, is now traversable, and the thing has a time translation symmetry because it's the ground state of the combined Hamiltonian. So that would be what the geometry would look like. That's how it works in the 2D case. So the geometry will look like this thing times the S3, which is non-contractible, like in the two-sided black hole, but that configuration, of course, has this configuration. The ground state is zero temperature and there's no horizon. But there's no horizon not because it looks like global ADS. It has the same topology as the two-sided black hole. It just metrically doesn't have a horizon because you can causally get from one side to the other. Oh, no. I mean...
No.
No. I mean, by you trying to achieve what?
Maybe you can say forever on one, but it makes the ground
Yep. Yeah. I mean, that's one reason to be interested in this alpha. That wasn't what I was discussing today, but I mean, the reason why I discussed the alpha today, the discussion today was a little different because we wanted this averaging, and we wanted to find the Euclidean solution also at finite temperature. Now we switched to talking about the ground states. So these discussions are slightly different. The Lorentzian continuation of the thing with finite temperature, and the alpha will probably not be traversable, but it's a connected Euclidean saddle once you include the one loop correction.
No, but the wire should be made out of spaghetti.
No, it's external. I mean, I added this coupling by hand.
Yeah.
I added this coupling by hand.
But have the dictionary.
We use the dictionary.
Double trace operator for the single theory.
It doesn't matter. It doesn't matter. I mean, the dictionary just says that the dictionary just says that the. No. When you add double trace interactions, it doesn't turn on sources. It changes the boundary action or the boundary conditions, right? It doesn't add a source classically. It just change the boundary condition. I mean, actually, you can always say it like that. When you add a single trace, you change the boundary action by something linear, which shifts the saddle. If you add double trace, it adds something quadratic to the boundary action, so I change the boundary condition. If I added something to the 10th power, we'll make a boundary action with the 10th power, and it will more nonlinear.
Double trace, it's like adding single trace operator with some random field and then averaging on this random.
Yes.
Adding a single trace operator with a random field is like now exercising some supergravity mode or
Mm-hmm.
That random field is going to the asymptotics.
Sure.
Doing supergravity, and then I'm averaging of some kind of boundary conditions.
Well, again, you can. so there, right. But I mean, there are two ways that you can analyze that situation, depending on whether you do the integral first or you apply the dictionary first. Right? Oh yeah. So